morning class and welcome to our continuing lectures on climate dynamics, climate variability and climate monitoring. In the previous week, we started our discussion on climate monitoring through various sensors systems. So this week we will continue on that vein and complete many of the in situ and upper air sensing systems that are used for measuring various climatic and meteorological variables. So today we will start our discussion with measuring an important climatological and meteorological parameter, wind speed and wind direction. First, we will discuss wind speed and then wind direction. Now, wind is a vector, and in most instrumentation, the horizontal component is the one that gets measured. That is, the east-west component and the north-south component. As you know, these are called the zonal and the meridional components of wind speed. U is the zonal velocity, which is positive for west to east moving wind. V is the meridional velocity, which is positive for south to north moving wind. The magnitude U is the total horizontal wind speed, which is the square root of U square plus V square. And the direction can also be obtained as tan inverse of V by U with respect to the north. There are two measuring systems, one for measuring wind speed, and these are called anemometers, and the other for measuring wind direction, and these are called wind vanes. Let us discuss the anemometer first. The most common type of anemometer that you may have seen in many places is called the cup anemometer, and the picture is on the right. As the name suggests, it's made up of three hemispherical crevices or cups that are attached at equal distances from a vertical shaft, which is free to rotate. The vertical shaft rotates on a bearing arranged to cause little to no mechanical loading, so that even small wind speeds can keep this shaft rotating. One thing to note is the cup arrangement is asymmetric. It is something that we do not see here, but basically they are not symmetrically placed along the 360-degree angle. It is skewed towards one side of the 360-degree angle, and this is done so that the anemometer always rotates in one direction, even as the wind speed changes from one way to the other. The response characteristic of the anemometer can be deduced. We will not discuss the deduction here, but in general, the angular speed of the shaft in radians per second is proportional to the wind speed U minus a constant U0, which is the starting speed of the anemometer. So what this means is, this is the minimum wind speed that is required for the shaft to start rotating. So if U is less than U0, basically omega is 0. Alright, so it is only when U is equal to or greater than U0 that the shaft starts to rotate. Now, there are two different applications. In climatological stations, usually larger anemometers are used because these have to be placed in locations and set for many and need to be robust to even storm speed winds. So these have a bigger starting speed of U0 of about 2 meters per second. So these anemometers cannot measure wind speeds which are lower than 2 meters per second. However, in micrometeorology, where rapid response is needed, light anemometers with quick response and faster, lower starting speeds are used. these have U0 of 0.5 meters per second. The response time of these anemometers are also important because wind speeds can change very quickly. So we need to know how long does the anemometer take to pick up a change that has happened in the wind speed magnitude. The response time is proportional to the inverse of the velocity of the wind. So, higher the wind speed, shorter is the response time. Lower the wind speed, longer is the response time. So, suppose you initially have a wind speed of say 5 meters per second, and that wind speed changes by 1 meter per second. Then the response time is proportional to 1 by 5. However, if you had the wind speed of 10 meters per second and that changed by 1 meter to 11 meters per second, then the response time is proportional to 1 by 10. So, it will detect the change in the wind speed much quicker the faster the wind is. Hence, it's measured in terms of the response length tau into u. Because tau into u, if you put u in this side, is a constant for a given anemometer. The proportionality constant is itself dependent on the size of the anemometer system itself. So, for large cup anemometers, where U0 is also large, the proportionality constant is around 10 meters. So, tau u is of the order of 10 meters. What this means is tau is proportional to 10 by u for large cup anemometers. Hence, is equal to 10 by u for large cup anemometers, where u is in meters per second. Hence, suppose the velocity of the wind at the location is 5 and tau u is 10, then a change in wind speed will approximately take 2 seconds to register. Alright. However, for light anemometers, tau u is 2.5 meters. Hence, if the wind speed is 5 meters per second and you have 2.5 as the constant here, then a change in wind speed from 5 meters per second will take 2.5 by 5 or half a second to register. So, you get a faster response with light cup anemometers. But the trade-off is light cup anemometers are relatively fragile and hence they may get damaged mechanically much quicker due to bearing wear, mechanical stresses, etc. The output signal is a voltage proportional to the rotational speed of the shaft. Often, the shaft is attached to a very small DC generator, which generates a certain electrical signal whose frequency is proportional to the rotational speed of the anemometer shaft. And then that frequency helps us to evaluate the angular frequency omega of the shaft. As a result, we can get the wind speed knowing k. Another option is a series of electrical pulses. So, this is a digitized format generated at equiangular sweeps made by the rotating shaft. So, for example, it is possible the switch turns on after one single revolution. So, suppose the shaft is rotating at 50 revolutions per minute. So, the switch will turn on 50 times over a minute of duration. And from that we know that what the shaft speed is 50 rpm, convert it to radians per second and get the wind velocity. Another less used option is a sonic anemometer. This is the figure of a sonic anemometer. So let's try to understand how this works. Here what we have is an ultrasound emitter, a microphone that emits sound at ultrasound frequencies 40 to 100 kilohertz. This emission of sound comes from this microphone, say it goes here where it is received and also reflected back. Alright, so the sound hits this receiver where this receiver detects when the sound is hitting this sensor B, but also the sensor B reflects the sound back towards the emitter A. And then the emitter A also has a receiver which detects when the reflected sound comes back to the source. So here what we are trying to find is the time required for the pulses of ultrasound emitted at 40 to 100 kilohertz to travel forwards and backwards between two fixed transducers. These two are separated by a distance of around 10 to 20 centimeters. Now, and this is kind of the figure. So this is kind of open to the atmosphere, so the wind can move freely through this system. So suppose now the wind velocity is in this direction. See the wind velocity V here. So the actual speed of sound will be the speed of sound in still air, which is Cs, plus the wind velocity V as it moves from A to B. Alright. Now if it moves back towards this side, here the wind velocity will be the speed of sound in still air Cs minus V. So T1, the time it takes for the sound to move from A to B, is the distance L by Cs plus V, and T2 is the time required for the reflected sound to move from B to A, is L by Cs minus V. You take these two together and you solve for V to get L by 2 into 1 by T1 minus 1 by T2 as the speed of sound. So if the time between emission and reception of the direct sound and the reflected sound are accurately detected, this is a way to get the component of the speed of sound in this direction where A and B are oriented. And what you can do then is have a separate orientation in 90 degrees to this to get the other component of wind speed as well. So sonic anemometer does not only give the magnitude, it can also give the component wise values of the wind speed in the zonal and the meridional direction. And here you can see this in this case, that you have one set here and another set here oriented at 90 degrees, so that the zonal and the meridional wind speeds can both be detected, and hence we are getting the wind direction as well as the wind speed, which is one of the great advantages of this sonic anemometer. Another advantage of this sonic anemometer is that it can also give the temperature of air, because the speed of sound in dry air is basically gamma, which is Cp by Cv of air, ideal gas constant of air, temperature of air by the molecular weight of air, which is of the order of 403 into T. T is in Kelvin. So if the speed of sound is known, and you can get the speed of sound by, once you know V, you can get the speed of sound from these equations. So if the speed of sound is known, then you can get the temperature of air at the same point. Important to note that moist air needs a correction, because the speed of sound is not the same for dry air and moist air. Hence a hygrometer is also installed in such devices to have a moisture correction for moist air. Another advantage is measurements can be done very rapidly. 5 to 100 Hertz rates, and hence it is useful to measure turbulent fluctuations in wind. Okay, so you can get also the turbulence that is present in the wind fluctuations. It is useful in the meteorological sensing. Also, if you remember, turbulent fluctuations or the can be used for rapid meteorological analysis of the wind. So that is the sonic anemometer, which is a more sophisticated kind of anemometer that is giving us wind speed, wind direction, temperature of air, as well as the turbulent or fluctuating components of the zonal and meridional winds. Next comes direct measurement of wind direction, and this is done through wind vanes, and this is a typical wind vane that you can see. Basically, it's a kind of a flat vertical plate which is attached to a horizontal arm that is able to rotate on a vertical shaft. So again, this is often put in along with the cup anemometer or on a separate. So these two look to be the same shaft. That is not true. This is one shaft and this is a second shaft, and the wind vane kind of rotates in the direction in which the wind is blowing. So unlike a cup anemometer that always rotates in a single direction, a wind vane rotates in the direction in which the wind is blowing. It basically gives by the dynamic pressure of wind on this plate is half rho, the density of air, into u square, the wind speed, which causes a static force on the plate, moving it till it is aligned with the wind direction, and then it stops moving. So you have a flat plate, right, like this, and the wind is moving like this. It goes till the plate is parallel to the direction of the motion of the wind. Then there is no further force and the wind vane stops moving. And this way, the direction of the wind can be determined. Now, obviously, this can be done manually, but in sophisticated systems, an automatic wind direction measuring system is installed. It can either be measured using a mechanical switch with multiple contacts distributed evenly around the shaft. So you have a kind of a 360-degree circle, you have multiple switches. So whenever the wind vane shaft moves by a certain angle, some of the switches get hit and other switches do not get hit. So based on what is the last switch that has gotten hit by the movement of the shaft in the wind vane, you can know what is the orientation of the vane, and based on that the wind direction is evaluated. Another option is an optical encoder with a digital signal corresponding to the measured angle of the arm with respect to a reference direction. So suppose the arm kind of moves and sweeps a certain angle theta with respect to a certain reference direction, say the north direction, and the wind vane is oriented at an angle theta with respect to the north, then that angle is measured using an optical sensor which gives a digital signal. Another option which I have shown in this figure here is a potentiometer. So this is the direction of the wind vane, for example, and this is a circular wire fundamentally with multiple resistances in series, and this is kind of a short circuit. Okay, so what comes is, suppose this is the positive terminal, this is the negative terminal. So here the total distance the current travels is up to this point, then it kind of moves here and goes out here. If this arrow moves further, then the electrical signal will move further downwards, and hence the signal will change, right? The voltage signal will change as there are more resistances on the way for a fixed current. And this kind of gives an idea of the direction in which the wind vane is oriented. It is important to couple wind vane with anemometer readings, as in calm conditions, wind speeds close to zero, the wind vane simply gives the direction of the previous wind and needs to be discounted. Okay, So if the speeds are very low, the wind vane does not move at all. So those measurements have to be discounted, and that is why you need to couple an anemometer with a wind vane, and has been shown here. Now we have found the wind direction and wind speed using anemometer and wind vane. Let's not consider sonic anemometers where everything is obtained at once. Just a typical cup anemometer and a wind vane. How do you evaluate the information there? Now, wind direction is conventionally defined as bearing of a point from which air is blowing. Okay. So, here if you look, the wind is blowing from the northeast direction towards the southwest direction. So, this is a northeasterly wind because it's blowing from the northeast direction. So, here the angle is theta. The opposite, a wind blowing from southwest to northeast, is a southwesterly wind, and here the angle is, if you can see, theta plus 180. Okay, this theta plus 180. So, this new theta is equal to the old theta plus 180. Okay. So, the direction is very important. So, the zonal west to east velocity component, for this case is minus u sine theta because it's going in this direction. See, it is going from east to west. So, it's a negative component, right, for this situation here. And the meridional south to north velocity component is minus u cos theta, south to north. So, the zonal component west to east this way. So, this component here is on the opposite side. So, you have the minus sign, right. Similarly, south to north is this way. This is the opposite side again. So, this is again minus u cos theta. This is theta, this is theta. So, this is u cos theta. This is 90 minus theta. So, this is sine theta. Alright. So, for this wind velocity, you can see that the zonal component is minus u sine theta and the meridional component is minus u cos theta. And the mean is integral of this over a certain amount of time. Is this also holding for the other case? So, here you can see the theta is now more than 180. Okay. So, this is 180, this is 90, this is 180, this is 270. So, here theta is basically between 180 and 270. Alright. So, again if you put the values, you will get the correct. So, here sine theta is negative. So, negative cancel, you will get positive u sine theta, and cos theta is also negative. So, you again get a negative. So, you get a positive value of u cos theta. Okay. So, you can do it yourself and see that this formula is valid for all possible cases of evaluating zonal and meridional velocity components. So, this is the general formula that is applied. So, whatever be the angle theta measured clockwise with respect to the north direction. So, suppose the wind vane is measuring the angle theta clockwise from the north direction, and u is the cup anemometer based velocity magnitude, then the zonal is minus u sine theta, meridional is minus u cos theta, and the means are this, and the average wind direction theta bar is tan inverse of this. Alright. Okay. So, we will stop here today. In the next class, we will discuss a very important part, which is wind measuring radiation. Okay. So, thank you for listening.